we are going to study the phenomena called interference. Mainly we are studying here the interference of light waves, and this is the outcome of the phenomena called superposition of light waves. So the topics will be covered here are the division of wavefront and amplitude case, Young's double slit experiments, Lloyd mirror frame biprism, and then the thin film cases, and the fringes of equal inclination and fringes of equal thickness, and lastly the Newton's ring will be discussed. So first start what is coherence, because it has a very important role in forming the interference. Coherence means if two sources which vibrate in a fixed phase difference are called the coherent sources, which will be understood by the following example. See, there is a two source S1 and S2, and the displacement produced by these two sources are y1 and y2, written here, where the phase differences between two sources are phi. So for the time being, don't think of phi as a constant or as a function of time. It will be both, or it will be neither. It will be both or either. Both means I should not tell both. It should be either constant or a function of time. I will come into this discussion later. So the resultant displacement will be y1 plus y2, and by doing cos c plus cos d formula we will get this formula. And here you can see this part is the amplitude part, because no time is involved here, as omega t part is not there. So this is the amplitude part, and if you take the square of the amplitude, you will get the intensity of the resultant displacement or resultant wave. So it will give you 4I0 cos square phi by 2, where I0 is equal to A square simply. So the intensity corresponding to the independent sources. So now let us consider the maximum minima of this function, and you know that if phi by 2 means phi, if you take phi as odd multiple or even multiple here, because cos square is there. So if you take phi is equal to n pi, then not n pi, sorry, phi will be the even multiple. If you take the even multiple, that is phi is equal to 0, or phi is equal to 2 pi, or phi is equal to 4 pi, then it will give you plus 1. That is the maximum value, because cos square is here. And if you take phi is equal to 3 pi or pi, for example, pi, so cos will be 0. 3 pi, then 3 pi by 2, cos will be 0. So the intensities are minimum for those cases. Those cases are written here, and so the intensity will change with respect to the phase difference phi. And here one can observe the intensity when he is doing a practical. Then he will observe the 4I0 into cos square phi by 2, because the phi, if phi changes, then he will record at average value. Always a changing thing, if you measure changing quantity, that is here, let us take an example, the phi is changing with time, then one can record a averaged value for that time varying thing. Here cos square phi by 2 is that thing. So cos square phi by 2, the phase, the average value, how we can measure it or deduce it. So let us take an example of ft, a function of time. The average value is 1 by tau integration minus tau by 2 to integration to plus tau by 2 and FTD is a very well known mean formula or average formula. And here what is tau? Tau is the time over which you are averaging, that is over which the experimental time is tau. So now if you record the interference pattern, that is resultant wave, in the normal eye, naked eye, then you will be able to see a frame for a time 1/10 second. If two frames come in between 1/10 second, we can distinguish those two frames by our naked eye. It is called the persistence of our vision. And if you can catch this picture by a camera whose exposure is 0.001 second, that is in between 0.001 second, you can record two consecutive frames, that is you can click two pictures with a time gap of 0.001 second. So clearly if phi varies in a random manner, then random manner in times which are small compared to tau, that is in case of naked eye measurement it is less than 1/10 second, or for the camera measurement 0.001 second. So then the average value will give you half. We know that thing, that average value will give you half. So cos square average is half. So half, if you put this half here, then 4I0 into half will be 2I0. And this is very interesting result, because 2I0 means I0 plus I0, and I0 is the intensity for the first source, and I0 is also the intensity for the second source, because the amplitudes we have taken here are the same, A and A. So the general illumination results in that means there is no interference. The definition of interference, we know that the periodic arrangement of bright and dark cases, in case of the light, or we can say the maximum and minimum intensities would be recorded respectively for interference fringes. It is a periodic arrangement of maxima and minima, but here you can see in the equation number 16 that there is no maxima, no minima. The result is 2I0 simply. So what we got, this condition came into the picture because of the fact that we assumed that phi is a function of time and which is rapidly varying, and phi is the phase difference between the two waves. So if the two waves are consisted of having a phase difference which is a function of time and which is rapidly varying than the measurement time, then the interference pattern will vanish, and this is called incoherency, and those two sources will be called then incoherent. If you keep the phi as a constant term, then the interference pattern will be there, because there is no point in taking cos square phi by 2 an average, because cos square phi is by 2 is a constant thing. So you change phi as you wish, you will get the maxima or minima in the intensity I, but not dependent on time. So this is then the cases will be called the coherency case, and the sources are called the coherent sources. So this is the fundamental thing we have to keep in our mind. We have to produce always a coherent source. So interference of light wave, the discussion is on these things. Say, consider this picture where two different sources are used, and two different sources, even if you take two same kind of candle or same kind of light sources, say two LEDs having the same power, but the light are coming from the sources as a result of atomic transitions. So atoms emit light, and we know that we don't know, we can see that atom in the period of 10 to the power minus 10 second will emit a pulse of light. But if we use two different sources, even in a single source, the two atoms don't have a fixed phase relationship. Yes, they emit light within 10 to the power minus 10 second each of them, but their phase relationship is not a constant with time. And in between two different sources, the phase relationship between the lights emitted from those two sources are very much different and very much time dependent. So they are not coherent sources, as we have discussed in our previous section. And Thomas Young in 1801 made such an arrangement which can produce a set of coherent sources with very ease. How? Let us take a source S and place a screen in front of it and make two pinholes S1 and S2 with a distance D. Then the light coming from S will be divided into two parts at S1 and S2. And we know the Huygens principle. The wavefronts are created and the wavefronts are propagated through space with respect to time, and some wavefront will be cut in S1 and S2 pinholes. See this picture 14.7. You can see there are so many wavefronts are generated, and a single wavefront, you can see here, the single wavefront is this one. Okay, this one. This wavefront is cut into two parts on S1 and S2, and a wavefront, and on the wavefront each points are new sources of disturbance according to the Huygens principle. So the S1 S2 point will emit again new wavefronts, and these wavefronts will interfere to each other to produce some interference pattern if possible, because the wavefronts will interfere to each other in phase or out of phase, depending upon the phase relationship. If they are out of phase, then it will produce a dark fringe, and if they interfere in same phase, then it will produce light, or that is bright fringe. So the sustained interference is achieved here with respect to time, because those two sources, new sources S1 S2, are the part of same source S, and same wavefront they are receiving. So the initial phase difference between two are just same, either 0 or the constant, and this will kept constant as the wavefront propagates from S1 and S2 and interfere in the forward region. So we can now mathematically formulate the intensity of the superposed waves. Let us take an example of S1 S2, and that picture is simplified here. The Young's picture is simplified here, and we place a screen LL prime here at the distance capital D from the sources, and the sources are separated by a distance small d to each other, and S is the original source. You can forget about it because you have two coherent sources S1 and S2, and the geometry is described here. This is the z axis, and the screen is along y axis, and x axis is perpendicular to the point O, that is the plane of the paper, of your paper. So the screen is just the xy plane, and z axis is perpendicular to that. So if we consider the light waves coming from S1 to reach P and S2 to reach P, the electric vectors at P will be E1 and E2, and they can be written as this because they are electromagnetic waves, and they are plane progressive electromagnetic waves. Here they are assumed as plane progressive electromagnetic waves. So cos kx minus omega t is there. Not x is written, S1p, that is the distance, and here the S2p. And see one thing, it is along I cap, and E2 is along I cap. Why I cap? The wave is propagating along the nearly z direction, because the point P is very close to the point O, that is central region of the screen is under discussion. And another fact is the small d is very less than the capital D. So the sources are very close to each other, so that S1p and S2p will be in the same direction. But the question is, the light is moving in this direction. You can assume that this direction is z-axis, roughly you can assume. But why the electric field is along x-axis? It is a fact that electromagnetic wave is transverse in nature. So its electric field and magnetic field, which constitute the electromagnetic wave, are in the perpendicular direction to the propagation of the light wave or the electromagnetic wave. It is a topic of electromagnetic theory, so I am not going into this. You just remember that electric field and magnetic fields are perpendicular to the direction of propagation. The direction of propagation here is the z-axis, so electric and magnetic fields are along the I-axis, or j-axis here we assume I-axis. So they can be added up to get the resultant pattern, and here again the cos, the geometrical formula is there. You can divide it into two parts, or otherwise you can just take a whole square of this, because we are interested in intensity, which is k into E square. K is a constant, universal constant, and I is the intensity, and E is the resultant wave amplitude. So it will be squared up, and this will give you the four terms: the first cos square, second cos square, third cos, and the fourth is again cos term. Now we know that optical beam has a large frequency in the order of 10 to the power 15 hertz, that is per second. So the wave changes its shape per second by 10 to the power 15 times. So it is a very rapid thing, and if one measure the intensity practically, it will measure the average value of each term which involve the time. So cos square omega t minus theta is there. Say theta is this part, okay. So cos square, or otherwise you can say theta is this part. In this case theta is this part. So theta is the constant part which is not dependent on time. So cos omega t minus theta, and this is another cos omega t minus theta part. Here it is a cos of a constant term, and here again cos of 2 omega t minus theta is there. So we have to evaluate three averages: cos square, and cos. This average is meaningless because it is a constant term. So now let us first do the cos square, and the minus t to plus t, again the formula we have written previously. And here you can see that there is some algebra is there. Cos square 1 by 2 is multiplied, so that we can use the multiple angle formula. And the tau, what is tau? Okay, let us come into that point, and the integration will result in half the first term, and the second term will be this. Don't put this 0 directly, because tau is not the time period. Time period is capital T, and you are integrating over the tau. Tau is much larger time than t, because t is just 2 pi by omega, which is 10 to the minus 15 order, in order, the order of the time period for the visible lights are in the range of 10 to the minus 15, and you were observing not into the 10 to the minus 15, because we have previously seen that if we record by naked eye, we can record in 1/10 seconds. So 10 to the minus 1 second is tau, or by camera 10 to the minus 3 second will be tau. So t by tau will be very less number, because 10 to the minus 15 by 10 to the minus 3 is equal to 10 to the minus 12, it is very negligible. So t by t is very negligible, that is why this term will be 0, and the cos square average will be tending to half. Similarly, you can do this integral cos 2 pi 2 omega t minus phi in the same manner. You will give the zero result similarly as we have done here. So let us go to the formula. I is equal to, so this will be half, this will be half, this will be constant, it will remain here, and this will be 0. So half k into E01 square may be assumed as I1, that is the intensity coming from the first source, and similarly for the second source is I2. So it is written here, I is equal to I1 plus I2 plus 2 into root under phi 1 I2 into cos lambda, where lambda is that constant part which is not averaged here, 2 pi by lambda into S2p minus S1p. S2p minus S1p is the path difference, between the rays coming from S1 and S2 and interfere at the point P. So consider this formula where of resultant intensity, where delta is the phase difference at the point P. You have measured this intensity at the point P. So delta is the phase difference at the point P between the waves, which involve the path difference between the waves multiplied by 2 pi by lambda factor. Okay. So you can see cos lambda is a periodic term, and this periodicity not dependent upon time, it is dependent upon the position where you interfere, where you are measuring. So it can be +1, it can be -1, it can be 0 also. If it is +1, then I will be maximum. If it is -1, then I will be minimum, and those I max and I min are written here. And if those intensities are very much equal, then you can get the minimum intensity as 0, that is a pitch dark fringe will be seen, and the bright fringe will be more brighter. And the most important thing, when does the maximum and minimum conditions appear? So appear when cos delta is equal to +1, the maximum appear, that is a constructive interference, or the bright fringe appears. So then cos delta is equal to +1 means delta is equal to 2n pi, where n is equal to 0, 1, 2, 3. So delta, put the value of delta, you will get S2p minus S1p is equal to n lambda. So path difference will be n into lambda to get the maximum intensity, and similarly the path difference is n plus half into lambda, you will get the minimum intensity. Okay. And there is another thing, if the holes S1 and S2 are illuminated by different light sources, then the coherence will be disturbed, and as a result of fact delta will be function of time, and cos delta will be, average value will be 0, and then we will get the general illumination I1 plus I2. So in coherent cases, we have discussed earlier, the same features are seen here also. And there is equal in case of Young's experiment, which is the pioneer of the interference experiment in light. He used the equal intensity light, because the lights are generated from a single source. Okay, and the source is here, and those openings are very much small. So the lights emitting from S1 and S2 are very much equal in intensity. So I1 and I2 are nearly equal to I0, say in that case the resultant integer formula will be shortened up, and 4I0 into cos squared delta by 2 will be in result. And if you plot with respect to delta, it will give you cos graph, but in the positive axis, because cos square delta by 2 is a positive term. So cos graph in the positive axis, in the positive direction of y axis will be resulting, and this curve will be, it is not needed to discuss because it is very much straightforward. What we have seen here, you can see that at delta is equal to, that is phase difference, when 0, then it will give you the maximum intensity, that is a bright fringe. It is called central bright fringe. It is called central fringe, which can be observed at the middle of the screen, because delta is equal to 0 means path difference is 0. S1p minus S2p is equal to 0. Okay, here. So S1p is equal to S2p can happen only in a point, at a point which is O. S1O is equal to S2O. So here it cannot be possible. Here it cannot be possible to become equal lengths of two waves. Here only possibility is at the central point, so it is called central fringe. Okay, so central fringe is bright here, and then alternately dark and bright will be appearing in the screen. So the experimental results shows that there are two kind of pictures you can get. See here, y is plotted with respect to x. So if you increase the x, here you can see this is a actual picture. This plotted for d is equal to 0.005 millimeter when the slit separation is 0.005 millimeter, and you can photograph the interference pattern and you will see this pattern. See, at the central region there is a bright fringe, then after this central region there is another bright fringe, then dark, then bright, but the bright fringes are curved after some distance from the center. That is, within the central region, say in this region, you will nearly get the straight line fringes. Sorry, the picture is wrong here. In this very short region, you can see the straight line fringes, and afterwards it is just hyperbolic in nature. It is curved, and if you take these two sides, you can tell roughly that hyperbolic nature fringes appears here. So what is the reason behind that? And you can see when d is increased, that is 0.025, then the fringes are flattered, and although the length of the screen is different, here the 50 millimeter is plotted and here the 10 millimeters are plotted. So more number of straight line fringes will appear when you decrease the distance between the slits, that is d, small d. So we have to now encounter the shape of the fringes. Here is a very interesting physics on the shape of the fringes, and for this you need some mathematical formulation, background mathematical formulation are here written. And the first thing is equation of an hyperbola. You can see here, most generally I would like to tell you the equation of hyperbola. This is the equation of curve in 3D. See, x square by a square minus y square plus z square by b square is equal to 1. This is the hyperboloid. The shape of the hyperboloid is this, and if you take projections of this 3D curve into 3D surface into a flat plane, it will give you very interesting results. Say if we fix z, that is z is equal to constant, then it will boils down to x square by a square minus y square by b square is equal to some constant. Okay, this will be the equation of hyperbola. So if we take the projection, z is equal to constant means xy plane. So if we take the projection of this hyperboloid on the xy plane, it will give you a hyperbola picture. Okay, if one need to project in the yz plane, so yz plane is the horizontal in this case, in this picture. So if you take the projection of the hyperbola in the yz plane, where x is equal to constant here, and if we make x constant but greater than a, then it will be a positive value. So it will go to the right hand side, will give you negative value. So negative will be cancelled out, and y square plus z square is equal to some constant will be resulted, and which is the equation of a circle. So if you see here, if you take the projection of the hyperboloid along on the yz plane, yz is here, yz is the horizontal plane in this picture, then it will result in a circle. So these are the very interesting facts of graphs, and which can be used in the segment called shape of interference fringes. So let us assume that the path difference S1p and S2p is equal to delta. Okay, and let us place a screen where the Young placed the screen. Young placed the screen where the screen is placed in the xy, along the xy plane, that is perpendicular to the direction of the propagation of the light wave. Okay, so z is fixed there, and we put z is equal to capital D. See the picture, the distance from the slit, the screen is capital D, so we can put z is equal to D, as we have assumed that S1p and S2p is nearly in the along the z direction. So if we put z is equal to capital D, and the slit's coordinates are very much known to us, that is, and this is this, the coordinate of S1 is just simple 0 d by 2. Okay, and this is 0 minus d by 2 because it is downward, and the point P has the coordinate xy. Okay, xy, x comma y comma capital D. So z is equal to t. So using these coordinates, we can calculate S1p and S2p and take the difference between them. It is very straightforward to calculate this thing, the path difference S2p minus S1p and delta, say. So if you take now, this minus is taken in the right side, and this root is kept in the left side, and if you square them up, then the to the power half will be vanished, and here the square can be calculated, and it can be summarized and can be shortened up to form this formula, where you can see y square by some constant minus x square by some constant is equal to 1 can be written. So this is the equation of hyperbola. So hyperbolic fringes appear here in case of interference experiment by Young. Again, if you evaluate the value of y from this equation in terms of x, it will give you this value, y is equal to plus minus something into x square plus something to the power half. Now if you consider this, that x is very less than d square, then we can drop this x square out of the equation, and y can be plus minus constant, and y is equal to plus minus constant means the straight line which is parallel to x axis. see what we got here. Here we got the straight lines parallel to x-axis. Here also the straight lines parallel to x-axis, and if we move further away from the central region where x is not less than capital D anymore, then the fringes will be appeared in parabolic shape. So the theory very much justifies the experiment. The shape of the fringes will be very much observed very in consistent manner in case of experiments. And very interesting another thing, the fringes are called non-localized here. These are called non-localized fringes. Why non-localized? You can place your screen anywhere in space after S1 and S2 slits or point sources to get the interference pattern. You can place the screen, let me take you into that picture. Yes, you can place screen here along XY plane. You can get the straight line or hyperbolic fringes. You can place the screen along YZ plane and you will get the circular fringes. So whatever you need the shape of the fringes, you can place the screen accordingly. Now the calculation of fringe width, it is worthwhile to mention that there is an article called Shape of Interference Fringes of Young's double slit experiment. Very much it is published very recently in the Journal of Physics Education. You can find the shape of fringes in very much detail, and you can go through this paper. It is very important and valuable paper, I should say. So the calculation of fringe width. Fringe width means the distance between two consecutive bright or consecutive dark fringes. In doing so, let us start from the fact that maxima will happen when the path difference is n lambda. So S2p minus S1p is our n lambda in this case, and the p is the point of interference or the point of investigation, which is at a distance yn from the central point of the screen, that is the central fringe, central bright fringe, and d is the distance between the slit and the screen, and in between the slits the distance is small d. So let us go into this calculation. S2p square minus S1p square will give you 2yn d. It is very simple to calculate it, and S2p minus S1p will be 2yn d by S2p plus S1p. Now let us take an example. When small d is very less than capital D, then S1p and S2p will be very much in the straight direction, that is along the z axis, and you will put roughly S2p D in place of S2p and D in place of capital D in place of S1p. So it will give you 2D. S1p plus S2p is roughly 2D. Let us justify this result by taking an example where small d is equal to 0.02 centimeter and capital D is equal to 50 centimeter. Okay, and OP is equal to 0.5 centimeter. Now S2p minus S1p is the practical value, say the practical value, that is the values from this equation. Okay, so S2p square minus you can calculate S2p. S2p is what? S2p is the root over of this term, S1p is root over of this term. You can put this capital D, yn and small d from here, the values are given, so you can easily calculate them. And what will be the result? 100.005 centimeter. And if you put S2p as capital D and S1p as capital D, the result will be 2D, and 2D will be what? 100. So after this integrating result, you got 100.005 centimeter, and roughly you will get 100 centimeters. So we can lose some accuracy by an amount of 0.005 centimeter or rather I can say 0.005% will be errorful in our calculation if we put S2P plus S1P as 2D, 2 capital D. So it is written here, and the equation is simplified like this, and S2P minus S1P we know it is n lambda, so Yn is n lambda capital D by small d, and the consecutive fringes in the spacing of Yn plus 1 minus Yn, which results in lambda d by d. You will get the same result if you use the condition for destructive interference, that is the dark interference, dark fringes. You will get the same result of fringe width.